because that's a unitless function. Is that good?
Yeah.
Okay, is it rolling? Okay, so what should I start with? Energy or clustering? Clustering, let's start with clustering. Okay, so the inside of your calorimeter looks like the inside of a cylinder. Unless you're doing a sphere, then it looks like the inside of a sphere. Either way, a jet coming out to it hits some part and makes basically a circle, or an ellipse really, on the inside of your calorimeter. Now, the way that this works is maybe the best way, I've been thinking about the best way to argue, and this might be the right way to do it. This is the side view, okay? From the side view, this angle is called theta. Now, if you also do a front view, meaning you're looking down the detector, this is the circle, here is the beam pipe, then your jet is coming out like this, right? From the side view, this angle measured from the x-axis is called phi. Okay, so theta and phi are the two different angles we use. And this is how you can draw them. If you have a sphere, it doesn't change a lot. This looks like a circle instead, right? But the basics will all still work. Now, what I tell you though is that a cone is that a jet falls in a cone with a radius of 0.5 in eta phi space, which I think is the part that is confusing everyone.
Is that a constant?
No. Oh, 0.5?
Yeah.
0.5 is a constant, yes.
Okay, so that'll be the same for everyone.
Yes, everyone's at 0.5. Yeah.
Okay.
That's in the document. So in eta phi space, it looks like this. So maybe the right way to look at it is this. First, let's try this. First of all, you can pick actual numbers. It's easiest to say it's just a circle, right? In which case, phi here goes a total distance of 1, right? So you can say, okay, so this distance in phi goes from, let's make it easy. How about from 0 to 1 in phi? Notice phi is in radians, so 1 is some kind of arbitrary angle here, right? Okay, and then we can do the same thing from eta. Let's just say eta goes from 0 to 1. Now, I need to point out that eta, remember, is a relativistic invariant version of theta, right? Eta is derived from theta. The equation, again, is negative natural log of tangent theta over 2. So, because of this highly nonlinear quality here, a difference of 1 in eta is not a difference. You don't get that by scaling this directly. You have to calculate theta here, convert this to a value of theta, convert this to a value of theta, and then take the difference between them, because it's nonlinear. Okay, so that's how you have to do your conversions. Take a value of eta, convert it to theta, a different one, convert it to theta, then you can get a difference in theta. So this difference, 0 to 1, tells you that this part here, this, I call it delta phi, right? That's the width of the cone, is a difference between two phi's, right? This delta phi is equal to 1. Right? Because that's the delta phi is like the difference between these two. These are the two ends of the cone, right? Phi is the angle between them in this view. Okay, so delta phi equals 1. Now here, this thing has a delta theta. Now delta theta will not equal 1, right? Because the difference in eta equals 1. What that turns out to theta will actually depend on what the actual values of eta are. So for example, if you're going from 0 to 1 in eta, delta theta, I think I calculated as like 0.7 or something like that. But if you're going from 1 to 2, you will get a different number, right? Because eta is not linear at all. Okay, so you just do it by calculating. But anyway, you can calculate what delta theta is given the original eta values. You can calculate this by taking this equation and inverting it. If you want to invert it, it's 2e to the inverse tangent of negative eta. Right? Did I do that right? Or did I go backwards? Wait, did I do that? No, it's the other way. It's the other way. 2 inverse tangent of e to the negative eta. There we go. Yes? Yes. Yeah. Okay. So it's easy to convert from eta to theta. You just plug it in. All right. So to make this work, just pick values of phi and eta to start with. And if you want to, and if you do it in a spreadsheet or something, you can always change the values later and easily get another answer. Okay. Then what that gives you now is in this direction, you have a delta phi that you know. In this direction, you have a delta theta, which you know, which you can calculate. Okay. Now the next step is to convert that into actual meters. That's just a little bit of trig, but it depends on your actual detector, right? So you need to take the actual measurements of your detector at this point. So for example, you can figure, once you know this, I'm going to redraw this so I can see it better. We know there's a triangle with this cone here with a delta phi, right? Once we know this, you can that's a bit off center. Okay, you can actually you can do this in a variety of ways, but the easiest way is just arc length rule. You remember that an angle, in this case, the angle delta phi is equal to the arc length divided by the radius. That's the definition of a radian. You might have forgotten, but it's the ratio between an arc length and a radius of a circle. So you can calculate it. You can calculate the radius, you know, right? Given a radius, you can calculate what the arc length is. Technically, the arc length is curved and yours is segmented, but you know it's going to be close enough. It'll be fine, right? And again, I told you you're going to be making approximations here. So this number from here, you can once you know your radius, you can convert immediately from delta phi equals 1 to what that arc length is here, and that tells you how much room this dimension actually takes up in your detector, right? So this is a very abstract, like mathematical space. When you get it up to here, this is actually physically how much it takes up in your detector from a front view, right? And then from that point, from a front view, you can see, well, you only have so many of those that you can fit around here without them overlapping, right? Allowing you to make an estimate. Now, eta is the more complicated one, or eta slash theta is the more complicated one. This side view is more complicated. I will do the cylinder case because the spherical case is really easy because it looks like this, right? It's still not even that easy though. But let me talk about this a bit. But the spherical case would just look like this. You'd use that arc length thing again. For a cylinder though, you're not using arc length, right? What you're using instead is you have something, you have some delta theta here, right? Actually, let's do it this way. What you really have is you have two, like these are the two endpoints of your cone, right? And I said you just pick them. You pick them as eta, you pick them as theta, you transform them to eta. By the way, I just realized don't pick 0 for theta. Don't pick 0 for eta, because that will give you a theta of. No, 0 for eta is fine. Never mind. Everything's good. Don't pick pi over 2 for your theta. Dang it! Now I'm getting all confused. Hold on one second. Yes, eta of 0 is fine. Yes, eta of 0 is fine. It's going the other way that's problematic. Okay, fine. So you're going to get basically when you transform the etas into thetas, you're going to get two thetas now, right? You will have an eta 1 and an eta 2. Those will transform to a theta 1, which is here, and then a theta 2, which is here. Both, they're always measured from the z-axis, right? The difference between them is like your delta theta, okay? But since you need to project it onto a cylinder, you just need to do a little trigonometry. Now I'm afraid of cluttering it up again, so let me just redraw again. Just do one of these. If this angle is theta 1, here is the radius, which you know. So this is the part that you want to know, which is what is the z component of it, from how far is it in the z direction from the center, from the interaction point, from the center, right? Well, that means you're just using a tangent, right? So you just say, okay, tangent theta 1, if you call this thing z, then tangent theta 1 equals r over z, from which you can easily calculate z. Then you repeat that argument for the other theta. So now you have a different theta, which is theta 2, the same r, right? So then you can say tangent theta 2 equals r over, say, z2, right? A different z. Okay? If you do that, then you have this distance here is basically delta z, z2 minus z1. Right? And that's how much space it takes up in your actual detector. Again, right? So for a cylindrical case, you have to do a little trig to figure out the space here. Right? And to do the trig, you do each angle individually, and then at the end, you can combine it to find out what the difference is in z. You have to do them individually because it's nonlinear, so you can't do the difference till the very end. So now you have this difference in z. So now you have, look, an arc length in phi, right, which is a distance. You have a difference in z, which is a distance, right? You multiply those together, and you get a square, right? So these two together trace out an ellipse of some sort, right? Where one of these is this distance s that we calculated here, the arc length, and the other one is this distance delta z that we calculated here. This is now a real physical circle, right? You can calculate the area of an ellipse. It's straightforward. It's basically pi r, 1/2 of this times 1/2 of this. You can so it would be pi times s over 2 times delta z over 2, which is basically pi times radius 1 times radius 2. There might be one extra term of something in here. You can look it up to make sure. There might be an extra term you can check. But it's basically just like that. So you can find the area. Now, like I mentioned, maybe it would be better, you have to make some approximations here, so it might be better to just use a rectangle. That would be an overestimate, that is, say, to make the area a bit bigger, because you know you can't pack them in that closely, right? So you might estimate it as a rectangle or something, which would be easier to calculate anyway. Once you're there, now, you have a cylinder and you know its surface area, or you have a sphere and you know its surface area. This is again of the inside of your calorimeter, because the part that's important for a jet is when it smacks the inside, right? So from the inside of your layer of your calorimeter, you have a radius that you now have a circle, a physical circle, or ellipse rather, that you can work with. You know the area of the whole thing, you know the area of this, so to a rough approximation you can just divide, right? Now, there is a caveat that is important. That is, these circles in the eta direction, which turns into the z direction, if you actually do these calculations, when you do 0 to 1, it gives you a big circle. If you go, say, 3 to 4 in eta, you'll get a much smaller circle, okay? Circles that are even in eta become, are really big when when you're near, like, straight up and down, and they get a lot smaller when you're out here. So you probably don't want to take this big circle and use that as your basis, because then you'll underestimate it, because some of these guys over here are a lot smaller. So up to you what you want to do about that. There's plenty of things I can think of that would, you could pick something in between, you could average, you could do a few different samples, however you want to do it is up to you. But I just want to warn you that the phi direction is totally fine, but the theta direction, right, the z direction, changes substantially as eta changes. Okay, so my recommendation is set this part up in a spreadsheet and then plug in a few values of eta so you can see how the numbers change. And then you can use that to make some of your estimates.
For a sphere, would it really matter?
For a sphere, you still have that problem.
Oh, really?
Okay, for a sphere, this part is easier. It's more like this. But the delta theta is what changes. Okay, delta eta is always 1. But delta theta is going to change substantially as eta increases. It's going to get a lot smaller as eta increases. So you'll still have to look at that. Okay? I think that explains it okay? You have any particular questions? I'm happy to answer like specific questions, but right now I'm on tape, so if you think this answers the general questions.
So you said we don't have to do this for the hadronic calorimeter, right?
Right, because this is really just a question of area. This is a geometrical question right now for the clustering analysis. This is a geometry question, not about getting through the detector right now. So really you just need to do the inside layer that it hits. That's where all the important stuff happens.
You just have to do this for the inside layer of the EM.
Now, because the thing is, for your case, which I know is special, still the inside of your hadronic calorimeter still looks like a cylinder, doesn't it? Or does it? Is there empty space there?
I think, yeah.
Oh, if you have empty space, then it does look like a sphere. Then it's confusing.
Okay.
I would say go ahead and just do it as a cylinder.
Okay.
I think that's a perfectly fair thing to do. You're a special case. Most people's are either a cylinder or a sphere, right? So, so the main thing to watch out is the eta does change, or the theta size will change a lot. So do some calculations to see how that happens. But aside from that, yeah, it's basically taking this thing, approximating a size, divide your total area by the area you think is the right thing to divide by, and that tells you how many of them you can fit, right? You can always, if you feel like, I do this approximation, but that seems a little too high or a little too low. Okay, well, take the answer round up or round down. You know, this is not like a final answer. It's an approximation. Okay, is that good?
Mm-hmm.
Should I talk about energy now? Okay, I'll talk about energy. If this is not relevant to you in this room, then I appreciate you bearing with me for a little bit. So here is the idea. You have here's what the way it works. This is your equation. X is on this axis. X is the number of radiation lengths. A easy way to calculate X is the distance, let's say the thickness, divided by the radiation length. Okay? So if you take a certain material of a certain thickness, then you take that thickness and divide it by the number of radiation lengths. The main thing to realize is if you have here's a picture of our detector, right? A bunch of layers of stuff. X is like a coordinate, like a position coordinate. It starts here, this is X equals 0, and then it only increases as it goes up. So it's not about the thickness of one layer, it's how far you are from X equals 0, which is the beginning of your colorimeter. Okay, so remember, X only increases, it never goes down. That's the main thing to remember. Now, these guys are made of different materials, so they will quite possibly have different radiation lengths, which is fine, right? So your X, so at this point, X, the number of radiation lengths might be 0.03, and like here it might be, you know, X equals 0.07 and so forth, right? You can have varying length, varying thickness layers and all sorts of things, whatever you want. But you're going to be increasing the number of radiation lengths as you go along. Okay, this graph is a graph of energy deposited versus radiation length. On this axis, technically, it is a number they call negative dE dx. Okay, it's technically what it is there, which basically is the amount of energy deposited per radiation length. But I've been sort of approximating that as energy because you do not need calculus to do this part, okay? And if you didn't know calculus, it probably wouldn't help you because you can't do this integral. So if you take the equation I gave you, there's a constant in it, A, which is, 1/2 natural log of E over EC minus 1/2 in this case. Plus or minus, but plus is for photons that I didn't ask you about photons, right? So it looks like this. A should be a constant. It does not change, okay?
But it changes between like the different materials.
Okay, so one thing it does change is it does change with the different materials because the critical energy is material dependent, right? So that is an effect that it has. I didn't actually look. How big is the difference in critical energies? Did you look? Is it not very different?
Not.
If the critical energies are not very different between your materials, remember, there's a natural log on this. But natural log, when you take a logarithm of something, it takes differences and compacts them dramatically, right? Because it goes by powers of e instead of by a straight difference. So if these things, if the critical energies of the two things are not crazy different, I would just use one of them. Probably your absorber, which does the bulk of the work, right? I would just take the absorber critical energy and just use that. Makes things a ton easier, does not really have an impact on the result, or a very small impact on the result. I would be totally fine with doing that. It is possible to interleave them and to calculate both of them, and if you've already done that work, that is great, okay? But if you're just trying to figure this out from the first set, you can just pick the absorber critical energy is probably fine to use. This E is always the original energy, which is the one that is basically your maximum energy, your worst case energy, if you like, that same as we use for the tracking one. So your center of mass energy divided by 3 is what you're going for. And then, so then you have an exponent A, which is not changing, okay? A becomes a constant now. And if A is a constant, you end up with something that looks vaguely like this, okay? There is a lump in it somewhere, and then it has a long tail. Warning, if you graph it in Wolfram alpha, it usually stops around here, and so it doesn't look like the hump. And it usually stops around here, that has another version that stops way over here, so it looks like nothing. So like the default Wolfram alpha graphs don't pick it. You have to set the bounds, which you can tell it to from whatever to whatever, and then you can actually see what the hump looks like. Do like 0 to 40, then you can see it. But it always does like 0 to 5 and then 0 to 300 or something like that. And so the default scales won't work. So just to warn you if you're using Wolfram alpha for it. If you use Desmos or something, of course, you can just zoom in. So here's the idea. What we are calculating is actually the area underneath this curve, okay? The area bounded by this curve. That is to say, the total area under this curve is 1. I've already normalized it, okay? So the total area here comes out to 1. And you're going to, but you're not going to go because that total area, this thing is an asymptotic exponential, falling exponential, so it's asymptotic. It never goes to 0, right? So you're never therefore going to reach 1. Right? That's impossible. You're going to reach some fraction instead. So the question is, how big a fraction can you reach? If you can reach 0.99, you are doing great, okay? 99% of the energy is a good job, and you can stop there. if you say what's the minimum, like people have various reasons they might be scraping to reach it. Your minimum would probably be 0.9. Okay, if you really want to hit above 0.9. And the difference between 0.9 and 0.99 is usually quite a few radiation lengths, so that can be substantial. All right, so how do you do this? You do this by, if you know calculus, this is basically a Riemann sum. But if you don't know calculus, it's fine. All you have to do is, we're basically taking each of these layers and drawing a little rectangle at that point. Okay? And we're going to sum up the areas of all these rectangles. So each rectangle has an area of the function, which I've been calling f of x. That's the complicated function I gave you, right? The x to the a times e to the negative x over 2 over all that funny stuff, right? So that's the function. That's the height of this, and then times this distance here, which I will call delta x. Delta x is the thickness, it's not the x coordinate, which is the thickness from the beginning of the detector. It's the thickness of just that layer. And it's the thickness not in meters, but in radiation lengths, right? So you do that same calculation on it to get it to radiation lengths. So this is the area of one of those rectangles. And then you just sum all of them up to where you stop, right? So I've heard a lot of people talking about number of layers. It's not about number of layers, it's about number of radiation lengths is what matters, right? Now, if you're using something like lead tungstate, which is totally fine, you have to break it up yourself into sort of your own like mental layers in order to do the calculation. Because if you try to do this with one giant rectangle, if your point is over here, it's not going to work. It's going to give you a completely wrong answer. So my quick experiments, I found that a thickness of 1 radiation length works totally fine. So if you go to 1 radiation length, then it works great. Above that, I haven't really tested, so I don't know. I know 1 radiation length works. So if your thickness, if you're doing something like, if you're doing individual layers, they should not be any thicker than 1 radiation length. That's actually already very, very thick. 1 radiation length of scintillator is 0.5 meter. You probably don't want 1 radiation length of scintillator. That's crazy. Usually they do, if you saw in the document, right, usually they're in like centimeters or something, right? Or a few centimeters each. That's the typical thickness. Like for lead tungstate, you can break it into units of 1 radiation length, would be perfectly safe. You might be able to go higher, I just haven't tested, okay? The goal is, if you go out to like 30 or 40 radiation lengths, you should be above 0.99. It depends on your exponent A, but at around 0.99, at 30 radiation lengths, you should be hitting close to 0.99, and by 40, definitely you should be at 0.99. Because this is logarithmic, it will go fairly fast. So this is the goal. Now, here's the goal. First of all, you figure out what's the total amount of energy I captured. That number, like I said, we want above 0.9, and if you can hit 0.99, that'd be great. Most existing detectors can hit 0.99. They usually push towards 30 radiation lengths. But some of them can't. Then the other question is, how much of that are you capturing? Now, if you're using a homogeneous colorimeter, the answer is 100%. But if you're doing a sampling colorimeter, which you'll have to for something, I'm pretty sure, then that question becomes because these are alternating, so you have scintillator and absorber. Scintillator, absorber, right? I'll label them SA and SA. So this is scintillator, absorber, scintillator, absorber. So this is your total energy deposited, and the sum over just the scintillators. So summing over the same thing, but doing it for just the scintillating material, that will give you the percentage of the energy detected. Okay, that will be a much, if you're doing a sampling colorimeter, that will be a much smaller number. Okay, it may be 20 or 30%, which is okay. It's the best you can do. Now, you want this number as high as you can, right? But you can't build a giant block of plastic scintillator. It's just going to be too big. It'll be too expensive. So this number you always want higher, but 20 or 30% is still fine. Okay, and so that's how you can calculate the total energy detected. That's for an electron. Then I say do it again for a proton. Great. For a proton, for the electron, the thing is this should happen by the end of the EM colorimeter, right? You don't move on into the hadronic piece. You should do it all in the EM and stop there, and that's how much you get. because the hadronic part is much coarser, not as good, it's not going to be able to pick up anything good from these electrons anymore. So you stop there. Then to do the proton piece, you do this again, but you use interaction length instead of radiation length. Everything else stays identical, including, and I'm sorry for that being clear, keep the critical energy the same. There is no critical energy for a proton given on those websites. That's fine. Use the critical energy for an electron. That's fine. It'll be close enough. There's a logarithm on it anyway, so it'll be close enough. So then so basically exact same exponent, but instead of counting radiation lengths, you would count interaction lengths. That will blow up all your actual distances, because interaction lengths are substantially longer than radiation lengths. And as a result, the hadronic colorimeter layers are usually substantially thicker. They're not that thick, by the way. They're typically like this thick, a few centimeters still. Then you just repeat the exact calculation, except with interaction lengths. For a proton, it goes through the EM colorimeter and then the hadronic colorimeter. So by all means, start with the EM ones and pick up that energy deposition, and then keep going into the hadronic one, right? That's you should definitely do that. You use the fact that you have the EM colorimeter there. That's all still measurements that you can take, right? But there's no way you'll have finished by the end of the EM colorimeter, you'll be like here on the curve, right? You will not have collected enough energy yet. So then you got to run through your hadronic colorimeter to really collect enough energy. So that's how you do the energy calculation. Once you've gone through this, it's virtually identical for electrons and protons. And again, I recommend doing it in an Excel spreadsheet so that you can just change the radiation length to the interaction length and everything else stays the same and you instantly get your new answer. Okay? So, any questions on that are kind of general? Okay, good. Well, as always, you can email me. People know that, right? Though, you know what? I'm going to bed earlier tonight. I've got like 4 hours of sleep a night for several nights, and I need to get some rest. I don't have I days and Saturdays like you guys do.
Oh, man.
So, all right, so you gotta